and that's how sensitive, how insane this camera is going to be. And you got dark field, there's no dark field taken, no flat field taken. Black level is at default. Live stack, everything is default. Okay, sounds good, Jack. To recuperate here a little bit, let me show what the settings are. Yep, if you go here and look at that, I don't even have the trigger mode on the screen. You can see to the left. Exposure time is 94 milliseconds. Here it is. In fact, we could probably go a little bit lower. Okay, how about if we go to, I don't know, 85.000. Let's try 85 milliseconds. And we still get N3. And the gain's all the way up to 50. So here I'm going to vary the gain a little bit. And all the way up. Now this is N3 live. Literally, so when I move the scope, you see this thing move instantly. And I am getting eaten alive by mosquitoes here tonight. It's cold, it's about 10 degrees Celsius, and yet the mosquitoes are just hungry. But anyways, yeah, the gain's all the way up. We got 85 millisecond exposure on M3. How insane is this? That is absolutely unbelievable. Now what I'm going to do is just scroll down. I didn't even start the trigger mode. And let me show you the bit rates. What we got is 8-bit. If we switch to 12-bit, we always lose sensitivity, which is normal. So leave it at 8 bits. It's fine. It's all what we need. And we've got the color adjustment, the hue, saturation, everything's at default. Okay. And the frame rate is set up to the lowest. If you increase the frame rate, you're going to lose sensitivity a little bit. So it's always best to leave the camera at the lowest frame rate for deep sky. All right, flip, rotate, sampling, digital binning. Okay, here we go. Let's see what 85 millisecond does if we digitally bin. Here, this is bin at times 2 at 85 milliseconds. That is absolutely insane, unheard of in the industry. Once again, I guess we're going to have another historical camera to be offered. Histogram is completely 0 to 255, so there's no adjustment there. It's all default. There's no dark field correction, none of it live, and flat field, there's no flat field either. And black level is at default, which is 2. And the conversion gain is left the way it is pretty well. It's not adjustable on this camera. You certainly don't need it. Live stack, there's no live stack at all. Nothing is enabled here, as you can see on the left. Normally if I'd stack anything, they'd be about 3 frames at most, but we're not using that tonight at all. And the sharpen is at default 0. If we increase that a little bit, of course, we're going to get a little bit noisier, but we're going to get a nice sharper image. And miscellaneous, the positive, negative, that's what it looks like. Drew. I think Drew is on. Drew Hulsick from 107.9 Coast FM. I believe he's on the list here this evening. If you want to come and stop by, Drew, you're more than welcome. And you could drive by the side of the second driveway and come out the back here with your car and just walk into the observatory. It'd be more than welcome to stop by, Drew, and watch to do the test with the cameras and various objects we're going to do tonight. So hopefully, Drew, if you do hear me, you're more than welcome. Drew lives out in Cardinal, not far from here, about 10 kilometers. So if you want to stop by, you're more than welcome to come down here and check this out. So let's go back here to what we were doing. And again, we're going to go over the parameters. The exposure 85 milliseconds. We're exploring this here, 85 milliseconds. This is unheard in history. And of course, the gain's all the way up. To get this kind of image, we need the gain. And this is the gain that we've remodified in this camera recently, again, this past week, and going really, really good at the moment. So we've got 8 bits. Let's recuperate what we're doing. 12-bit, you're going to lose always sensitivity with any camera. Color balance, pretty well turn down the green a little bit. And we can always go to default. But the green's a little strong, so just by lowering the green just a tad, you just bring that nice balance here. There you go. That's the only adjustment that we've done to the camera. Gonna lower it down a little bit more. There you go. Yeah, we'll do so in a moment, Jack. I just want to review what we're doing here. Color adjustments is complete default. Everything's at default. And the frame rate is low, as shown on the screen. Bit still bidding is at 1. Basically, it's off. This is 85 milliseconds. So if we go to times 2 bidding, it's insane. This is 85 milliseconds. This is how much sensitivity this thing is. So we're just waiting for it to get a little bit darker because we still have blue skies here, by the way. Let me do the adjustment here to the color bits like I had earlier. I think that's going to be pretty well right here. All right. Very sensitive in the green area. Most sensitive chip, that's what's going to happen. We still see nice colors in there. There's no question about it. And let me continue here. The histogram is stock. It's just the way it was. 0 and 255. So we haven't touched any of this. And we've got dark field correction. There's none. So the camera is displaying raw image live at 85 milliseconds. Here's a flat field. There's nothing. Black level is at default. And live stack, there's no live stack happening. It's not even enabled. This is live 85 milliseconds, folks. Unheard of in the history of amateur astronomy. Now, Jack wants me to try to lower the time here. It's 85 milliseconds, as you can see. And he wants me to put this down to 20 milliseconds. Okay. Let's try 20 milliseconds. Here's 20 milliseconds. Once again, this is unheard. And we're going to try digital binning times 2 at 20 milliseconds. And yes, you certainly do see M3. This is how sensitive this thing is. So now it's at bidding 2 Go binning 3, we are getting overexposed at 20 milliseconds. So let me go back at normal binning. And what we're going to do is pump up from 20 milliseconds, and I'm going to go back to 85 milliseconds. I think 85 milliseconds is pretty cool and pretty nice for what it is. And the gain's all the way up. Now, if we're going to go a little bit higher in exposure, that is unheard of, folks. I'm telling you, it's mind-blower. I redid the bias in this camera again this week. So this is the third time that I'm doing the broadcast with it to do a little bit of test. So what we're going to do is this. Let's go up to maybe 100 milliseconds. Yeah, we'll go 100. So this is 85. Let's go to 100 milliseconds. Oh, it's a little bit brighter. Okay, that's pretty cool. And what we're going to do is, let's go to 200 milliseconds. 200 milliseconds and it's overexposed. That is unreal. 200 milliseconds. It's not even a quarter of a second yet. Now if we lower the gain, we're going to get a much nicer image. If we increase to 250, let's add 50 milliseconds. Gee whiz, we're used to hearing let's add several minutes to a picture and see what's going to happen. Here we're talking milliseconds. And if I put the gain back up where it was, it's overexposed. 250 milliseconds. Okay, how about if we go 1000? So 1000 means we'll get 1 second exposure. No, not yet. Hang on. 500 milliseconds. Let's go half a second. It's overexposed. All right. The gain's at halfway at 25, so we're going to lower the gain at half a second. As you can see, the longer the exposure, the smoother the image becomes. Less noise. Nonetheless, we're still detecting colors in there, and that's what amazes me. So the gain right now is at 12.60. 12.6, and the exposure is 500 milliseconds, which is half a second. So the gain right now is set at 12. So it's not even a second yet. What I like about this and what we're looking at is we actually can detect colors in the stars that we're looking at the moment. And what that means to me is the camera sensitivity is one thing, it's the electronics associated inside. The electronics that's matching the actual sensor that was designed for that sensor. It's not the same as other cameras. But we need to deal with this extreme amount of sensitivity from the sensor. Okay, folks, just give me 1 minute. I'll be right back. I just got to step outside and turn it on because I think it's getting to be in the way of the telescope. I'll be right back. Hang on, folks. Okay. Okay. Here we go. We're back again. The telescope just moved a little bit, and we're still at half a second. Now this is live, and what I would like to do is go back to what we were earlier at 85 milliseconds, just to show those who just tuned in. All right, here's 85 milliseconds. Let's turn up the gain. This is 85 milliseconds. Jack, I don't want to zoom. I really don't want to zoom anything right now because of the size of the pixels, and it's just going to show stuff we don't want to see. So let me do the test that I want to do here at the moment. I'm at 100% right now of the image size, and I would like to leave it that way, and just so I could complete my test that I need to do here tonight. And yeah, this is a new prototype, Jack. Absolutely right on that. It's a DS287. It includes a IMX287c color sensor, but there's going to be a black and white sensor that will have nearly double the sensitivity. We're waiting for the sensors to arrive at the moment, and there will be a mono available. When you think about it, this specific camera has 4,589 millivolt output. This is the highest in the industry, bar none. The black and white version of the 287 is going to have 7,430, I believe it is, if memory serves me right. It is an absolute unheard of amount of sensitivity ever in any type of sensors. Now, my big test for that is going to be to compare that to an exterminator, for an example, that uses CCD, and it has the most sensitive CCD on the market at 3,200 millivolts. It also has larger pixels. The IMX287 has 6.9 by 6.9 microns, so it's a bit smaller, but the sensitivity of it is quite insane. And one of the things I really like about it is the ability to pick up the colors at such low exposure at 85 milliseconds. We're talking about. Let me reposition the object. As you can see, when I move it, it moves instantly. On my screen, there's no lag, there's no anything. So this is actual real live imaging that we're doing. Real live observations. There's no lag, there's no near real time has been going on. Of course, the technology has improved in certain ways. For USB camera, I have to say this is very impressive. And here's the best part, folks. This specific camera is going to be so affordable, and the amount of fun someone's going to have with this specific camera is unheard of, because of the amount of exposure that you could do with this and the sensitivity that presents itself. Yes, get the hell out of the way. What I don't understand, Oski, is on those EAA, on Cloudy Nuts, and those other so-called video forum, is they're the first one to bash our brands now. And all these guys used to have Mallin cams, and for some reason they just switched side and they decided they're going to hate Canadians. It's obvious that's what it is, which is fine with me, and because I'm not there to be liked or disliked, it doesn't matter. I'm here just to design cameras so I can observe with my aging eyes, so I will be able later to see stuff that I've never seen before still. And that's what pushes me to design those cameras. We always have the most sensitive camera in the world when it comes to video astronomy. Not one company has been able to come up and stack up to the exterminator at the moment. And good luck getting this one here. They're going to have a hard time to follow us on this one. Now the beauty of this is at 85 milliseconds, as you can see, a Dobsonian user, non-motorized, will be able to use this camera without tracking. Basically, they're going to be able to see live on the monitor, and they'll be able to push their Dobsonian telescope where they'll see the movement live, just like I'm doing now. On my screen here, this is moving instantly. There's not a lag. There's no near real time, as they call it. It is real time. This camera is a USB 3. Now let's go back to what I was showing here earlier, folks, because a lot of people are on now. Here's the exposure, 85 milliseconds. The gain on top is at 50 here. I'm going to bring it down about halfway. At about 25, that's halfway, and the gain's all the way up. Here's what I'm going to show you. The bit depth is at 8. Color adjustment, everything is at default. Everybody could see that. This is the prototype that I have, by the way. The frame rate is set at the lowest. Lowest frame rate. Digital bidding is turned off. This is digital bidding on. Obviously at 85 milliseconds it's overexposed. And this is digital bidding normal, which is 1. Histogram is stock. It hasn't changed. Basically it's defaulted at 0 and 255. There's no dark field correction involved. There's no flat field involved, as I'm showing. Black level is at default, which is 2. Conversion gain is not active on this camera. You certainly don't need it. Live stack is not active. The enable button is on there, and you really don't need it. Yeah, what do I do? I'm just curious to try this out here. Okay, that's what I figured. We need longer exposure to get the stack to happen, but that's okay. So there's no stack at the moment, and the sharpen is at 0, default. Okay, we can increase the sharpening and see how the stars get much tighter. And then the miscellaneous, well, we've got the negative. We could go negative if we wish. And that's pretty well it. Caption resolution, once again, 85 milliseconds. Whoop, there you go. Now here's the step we're going to do. So at 85 milliseconds, it's finally getting darker here. Hopefully the blue sky is starting to go away. We're going to change that figure here to 100 milliseconds, and let's see the brightness we're going to gain. So it's slightly brighter. We're going to change that to 200 milliseconds. Okay, now it's getting overexposed, and I suspected that because the gain's too high. So we need to bring the gain down a little bit. Gain on this camera is extremely important. The only two things you need to tinker with, if you wish, is the exposure and the gain. The longer the exposure, the less gain you got to use. That applies to every camera. Okay, now we're going to go to 250. So that'll be quarter of a second, 250 milliseconds. Well, there's less noise in the background, which is to be expected. There are no short exposures. And of course, if we turn up the gain where it was, it's overexposed. But here's the thing that I really like about it, and it's called dynamic range. I've changed the bias on this specific prototype. This is the 3rd time I do that. Even at low settings, high gain or low gain, we still pick up colors in the stars. So just imagine what that would do if you're looking at a cloud, for an example, like a nebula, for an example, or even a galaxy and things like that. That would make colors come out right away. It would pick up exactly what it looks like. So now we're going to pump that up from 250 to 500 milliseconds, which is half a second. Now we're getting serious. The noise has disappeared or getting lower, and it's overexposed. So let's drop down the gain from 25 down to about roughly 13. The gain I like on this camera is between 8 and 13, 15 tops. Okay, this is 500 milliseconds. We're going to go for 1,000. Whoop. A little bit too much here, isn't it? Okay, 1,000 milliseconds equal 1 second exposure. Here's what 1 second exposure looks like. Now we need to bring the gain down because it's overexposed. Alright, there we go. And the result we get if you lower the gain is you nearly get the same thing as what we had at 85 milliseconds, except we're getting more stars on the outer field surrounding M3. So I got to lower the gain out to 6.40. Well, let's go back to what we did. Michael just joined us. Michael from New Hamburg. Michael Byrne is the gentleman that does all of the manuals for all of us to read. And I tell you, nobody else could beat how he does a manual. So what we're going to do, just to show Michael, I'm going to 85 milliseconds, Michael. And I'm going to turn up the gain to 50. And here's M3 in real time. So Michael Burns, if you see that, check out 85 milliseconds, what it does to M3. This is so cool. That sounds good, Jim. Have a good night, Jim. Thank you for stopping by. Okay, so let's go back to, we were at 1 second. So 85 milliseconds, and let's jump to 1,000 milliseconds, which is 1 second. But of course, we're going to overblow this thing out of proportion. So we need to bring the gain down to about 6, maybe 7, 8, without blowing the core. Okay, Jim, send me the bill for your keyboard. I'll send you a new keyboard. Okay, now what this thing can do with longer is, so we went from 85. We're actually we were down to 20 milliseconds at one point, as requested by Jack. Let's pump that up to 2 seconds, see what it'll do. Wow, 1 second to 2 seconds is a major step. And here's the thing, it's overexposed. So what we're going to do is turn the gain down. Obviously this thing is hungry for light, so we're going to bring it down to 4.80. This is 2 seconds. The longer exposure we go, the less noise we have. Okay, now the gain is at 6, and we are starting to overblow blowing up the core of M3. So what we need to do is lower the gain a little bit more. Now the higher the exposure, the lower the gain's got to be set. So to give an example, we're going to go to 3,000 milliseconds, which is 3 seconds. What's the difference? 1 second makes, we're just overblowing the core. So that means we need to turn down the gain down again. We're going to go down to 4. It's still too high, so we're going to go down with gain 3. This is how sensitive this thing is. That's insane. But if you look on the outer shell, or surrounding M3, we're starting to detect a lot of the stars over there. Okay, so let's pump that up even higher than that. Let's go to 4 seconds and see how it handles the dynamic range and the oversaturation. We may have to go even lower on the gain, so we're down with the gain turned off right now. Okay, we need a bit of gain to bring back The dynamics into the image 2.60. So let's wait for that 4-second shot. Okay, we're right borderline of blowing the core, but we're still at 4 seconds and the gain's at 2. Here's the experiment we're going to do. Let's go back to 1 second and see how much gain we're going to need to increase it. Alright, here's 1 second. Let's increase the gain to about 13 or so. That's how I had it earlier, roughly 13. That's what I was saying. 13 seems to be the base that works well. And we're getting eaten alive by mosquitoes here tonight. But we also got more noise in the background. So having that noise simply is because exposure is too short. That's where the signal to noise ratio comes in. What is signal and what is noise? The calculation done inside the camera has to figure that out. So it's got to read every voltage coming off the pixel and determine, is it an actual signal or is it noise generated? And this is where the computation inside of the camera has to be done. Let's lower that again. This time we're going to go down to 100 milliseconds. Like we had it earlier. Increase the gain to 50. Yeah, we got a lot more noise, but we still detect it. Even at 80, 85 milliseconds. All right, my guess would be that 1 second seems to be a good round number. Let's go to 1 second. Let's bring down the house down. The gain's a little bit too high. We got a good, decent image. Certainly is better than what an eyepiece is going to give us. And this is what it's about. For those who have a hard time seeing, like me. We can increase furthermore. So how about if we went to, let's go 5 seconds. This time we're going to have to really bring the house down. We're going to have to bring the gain down. That's what I expected. Okay. We'll put the gain at 1.20. Alright, there we go. Let's wait at 5 seconds countdown. There you go. That's a nice smooth image actually. Because we have a greater signal to noise ratio, which means the exposure is longer. I'm going to turn up the gain to 1.25. Yes, Michael, I agree with you. It's a shame when 4 seconds is too long for an exposure. But Michael, true video observation, that's what it's supposed to be. The shorter the exposure, the better it is. Simply for those who have telescopes that are Altaz mounted or they don't track that well, or low cost type of telescope, this is where these cameras are going to shine. So we've got 5 seconds here, and we've got the gain set at 1.25. I'll try to turn up the gain a little bit more to 1.30 and see what she's going to give us. Okay, yeah, it's a little bit brighter. All right, let's keep breaking that up. 1.40. So we're going to fine-tune the gain here. Yes, it is a Graham. You could actually tell the colors in the stars. So we could actually see the colors in the stars. But if you go too long of an exposure or too much gain, you're going to overwash that color here. Let me show you a little bit. If we go gain number 2, oh, that's getting pretty nice. You could see some red stars, blue stars. There we go. The image is getting much nicer. Now, here's the thing. This specific sensor is the DS287. It's the world's most sensitive sensor. And why did Sony came up with this specific sensor is rather simple. It's for machine vision. This sensor is used for machine vision. That means manufacturers, any type of manufacturers, it doesn't matter what they're making actually, but we're going to use carrots. When thousands of carrots are going by, they need to be inspected for bad ones. They need a sensor or a camera, basically, that'll be so sensitive it will detect the bad ones right away and pop them out with air jets. And for that, you need to have a camera that is extremely sensitive in order for their computers to detect those bad carrots, for example, and pop them out of line. So a human doesn't have to do it. They could do thousands of them per minute that way. And that's what that sensor was designed for. Now, keep in mind, this is an industrial grade sensor. It's not your typical that you're going to find in an iPhone, an iPad, or fancy DSLRs, or cheap astronomical cameras from China, as I'm not going to mention any names specifically, but it doesn't matter. The point is this. Those sensors are made with a thicker wafer where the pixels are mounted on it, so they are made to run 24 hours a day for years on end. Years ago, I explained to you people that hopefully you remember the difference between a CCD and a CMOS. CCD would outlast any CMOS because they were made with a much thicker wafer and the way the structure was designed inside of them. Now they finally came up with this with the IMX287. It's built a little bit similar like a CCD. They're borrowing the technology of the CCD and they put this into a CMOS. Now the beauty of this very specific sensor is it's the only one that has external adjustments. That means if you design the circuit to match that specific sensor, you get to change the bias. Normally you can't do that on the CMOS. It's very difficult, if not impossible. You can only play with certain voltages and things like that. This sensor has parameters that are fully adjustable. So because of that, I was able to adapt the circuitry that I needed, that I used, that I designed to be adapted on this IMX287. Now, right now, the most sensitive CCD on the market is the ICX828, which we use in our exterminator. This guy's got, this specific CMOS has 4,589 millivolt output compared to 3,200 from the CCD. So we've got a ton more sensitivity, and the pixels are quite big for CMOS. 6.9 by 6.9 for a CMOS, it's huge. You need that to get that sensitivity. Now here's the best part. The black and white version of that, instead of having 4,589, it's going to have some 7,480 or 30 millivolt sensitivity. So what I'm showing you tonight is absolutely nothing compared to what the black and white's going to do. With the black and white, when we go down to 85 milliseconds or even 20 milliseconds, like Jack requested, we're actually going to have an image that is quite visible, and it will show in real time, not accumulated, not time exposure or anything like that. So as soon as the black and white sensors comes in, we're going to have a limited amount of them, and production of that will start. And I'll have to do tests on the prototype of black and white as well. So that's what I'm looking forward to do in about 3 weeks' time or so, give or take. But right now I'm doing the third version here. This is the third final version for the color one. I am using an MFR5 focal reducer with a 10 millimeter spacer. So we're getting a fairly wide field of view using a small chip. It's not a big chip. It's a 6.3 millimeter diagonal, so it's quite small. It's less bigger than the exterminator ICX828, which is half an inch diagonal, which is 8 millimeter. But if you use the MFR5 on it, you get to have really, really nice field of view. And the other thing that I really like about it is it increases sensitivity so much more. So that will be adaptable just about to any telescopes. So what we're going to do now, we're going to bring the house down to 1 second, and we're going to change object. All right, let's go back to 1 second. We're going to increase the gain, which is overexposed. That's okay. I'm going to leave the gain approach. That's terrible. 1 second and it's overexposed. So we need to lower the horsepower, or in other words, lay back that gas pedal in your car. It's pretty well the same effect. There you go. We'll leave it the way it is. I'm going to swing the scope on another target, and I'm going to be right back.
Was it the same? You're not gonna get it.